Hi everyone, Mrs. Besega here, and today we're doing the final review for 5470, the Unit 9, waves and sound, all sorts of thing. Now, where all waves come from are some sort of vibrating or oscillating source. So we started off the unit with talking about frequency. Frequency is the number of cycles per second. So sometimes you'll see me write this as like how many cycles occur per total time. So the number of cycles per second is called frequency. And the frequency of the oscillating source matches the frequency of the wave it creates. Next, a string is vibrating with a known frequency of 440. If the frequency doubles, the time period is going to get cut in half. The 440 is extraneous or extra information because you can actually answer this just from the other half of the problem. Frequency is inversely related to time period, and it's a perfect inverse with no like extra number up top. So if you doubled the frequency, it would cut in half the period. Both the frequency and period of the oscillating source create that wave. So a wave would have the same frequency and time period as whatever source created it. As this thing vibrates up and down or left and right, however we measure it, the amplitude is going to be the distance from the equilibrium point to the maximum or minimum. If this were a transverse wave, we'd call this a trough. But this could be the minimum of a pressure wave, and we would call that a rarefaction. So the amplitude is B, the distance from equilibrium to min or max. The time period is the total time over number of cycles, or you could also think of it as the time per one cycle. So I got D for this. It's how long does it take to go one up and one down, one complete cycle and back again. Number 5 is just a vocab question. Let's say I have a fundamental frequency. Let's say that frequency is 100. The next frequency up would be 200, then 300, then 400. And these sets of frequencies are called harmonics. The fundamental frequency is the first harmonic, because it's the loudest that you hear in an instrument. It has the biggest amplitude, it's the most obvious, and all the others are the harmonics. One complete cycle is one complete up and down. A to B does not complete the cycle because it needs to come back to its original position. But B to D does. B goes down, up, and starts and ends at the same place. So I would say for this one, B to D. Number 7 is a vocab word. Two large ocean waves come together to form a larger wave. Sometimes it helps to draw out the picture with this. This is called constructive interference. It's when the two amplitudes add together to make a bigger amplitude wave. Or like in this case, 1 plus 1 equals 2. Pitch is related to frequency. It's the note that we hear. For number 9, large horns such as tubas produce sounds with long wavelengths. So if the length of an instrument goes up, the wavelength of the instrument goes up. But that creates this frequency relationship because wavelength and frequency are inversely related. So I would not say A. That's not direct. If length goes up, frequency goes down. Wavelength of sound is inversely proportional to frequency, so it's not C. Pitch is another word for frequency that's still not directly proportional. It must be B. The wavelength of sound is directly proportional to the size of the instrument. And I could draw this out too. Let's say I'm doing a tube instrument like a flute, which is little and tiny. And I'm going to do the third harmonic. Oh, drew the fourth. Happens. If I took a tuba much, much larger and I did the fourth harmonic, the wavelength is much bigger for a bigger instrument because it has more space for these harmonics to fill out. So if the length of the instrument goes up, the wavelength goes up. The speed of any wave depends on the medium it goes through. For sound, that might mean making a hotter gas because hotter gas particles travel faster than cold gas. I could have the medium be a lighter gas, like helium. Sound travels faster in helium because the particles are light and easy to move. Sound travels faster in a solid because like the particles are close together so the collisions happen more quickly. Faster than in a liquid or in a gas. But the big idea for this question is that speed of sound depends on the medium it goes through. If you answered things that change the medium of the sound, that would work. For the frequency of a note played by a guitar string, frequency depends on a bunch of things. I'm going to take my wave equation and just rearrange it for a second. The frequency that you hear depends on the speed of sound and the instrument size that it's going through. So on a guitar string, I might pick a longer string. That might mean like taking your fingers off the fret so the string is longer, because that would make a larger wavelength. That would change the frequency to a lower note, lower frequency. I could change the speed of the wave. And this time it's not the speed of sound, this is the speed of the wave on the string. If I increase tension, that's changing a property of the medium. That would make a faster speed and a higher pitched wave. And you totally know this because if you were tuning a guitar, you would increase the tension, you'd hear the notes go up. Finally, you could choose a lighter string. If you looked at a guitar, you'd see they all have different string densities. There's some like heavy, thick metal strings, there's some light, thin metal strings. The lighter string has a faster transverse wave traveling inside of it, which would lead to a higher frequency. And since this question was kind of unspecific, it asked for like, how could you change the frequency? These are three changes, even though one is a lower note and the other are two higher notes. People got stuck on 12A because they were like, what do you mean by what type of wave is this? Um, I'm asking like, is this transverse or longitudinal? I'm hoping you'd recognize the shape is transverse because the wave is vibrating up and down as it travels to the right. So let's talk about that. The amplitude of the wave is this distance from equilibrium to max, or equilibrium to min. A very common error is to try to take this from top to bottom, but that's not it. It's the amplitude from equilibrium. So I'd say this wave is just over 4. So if I fill out the missing numbers here, that looks like the amplitude is 5 centimeters. Just like the problem on page 1, the time period is the time for one complete cycle. So 1 up and 1 down. So maybe for this, I do 1 up, 1 down, starting and ending in the same place. So the time period is from here to here. Now, that looks to me like 1.4 seconds, but if you got a little higher or a little lower, I'm totally fine with that. You can't directly get frequency from this graph. Frequency is the inverse of time period. So if you knew the time period was 1.4, 1 divided by 1.4 is 0.71 hertz. If I were to draw a wave with half the amplitude, then instead of going all the way up to 5 centimeters, I want to draw a wave that only goes up to 2.5 centimeters. And twice the period means it should take twice as long. It should finish a wave at around 2.8 seconds. So my new wave would complete its motion here, go up half as high, and take twice as long. So I'm going to try and max it out at 2.5 on both top and bottom. So half the amplitude, it's not as tall as it was before, but it takes twice as long. A standing wave is going to have a series of nodes, that's no motion, and antinodes, that's where the amplitude is the biggest. A common misconception is people will be like, oh, one wave must be one antinode. But that's not true. A wave is still one complete up and down, so my wavelength should be two complete antinodes. That's why when I do this equation in a second for wavelength, it has this 2 in there for seemingly no reason. The 2 is because it takes two antinodes to make one complete wave. It doesn't count the reflection over here. This wave is the third harmonic in the set because it has three complete antinodes. So that means in my equation, n is equal to 3. Now, before I go answer this problem, I want to show you that this equation says that one wave is 2/3 of this original length. Does that make sense? I'm shading in 2 out of 3 of these antinodes. That's why this equation looks like this. It's 2/3 of the total length of this instrument. And 2/3 of 0.9 is 0.6 meters. This standing wave is the third frequency in the set. So once I get this frequency based on the speed of the wave in the string, that frequency is not like the fundamental frequency. So D and E are not the same answer. Dividing this on both sides by 0.6 is 416.67 hertz. To get the first fundamental frequency is first frequency, I would divide 416 by 3. If having a chart like this helps you, as I know it helps many people to visualize frequencies, if I know the third frequency is 416 and they're multiples of each other, then to get that first frequency, I would take 416 divided by 3. That's what this equation on your equation sheet says, is the third harmonic is 3 times larger than your first harmonic. So for that, I get about 139 hertz is the fundamental frequency of this string instrument. If from there I wanted to get the second frequency, I would do 139 times 2 or times 3 or times 4. Tube instruments have the same exact patterns, still nodes and antinodes, except that there's antinodes on each end because that's where it's open to the air. To point it out, string instruments have nodes on each end because like maybe this is a guitar string, so you like put your finger right here and there's like, I don't know, the bridge of that instrument. This is the first harmonic because I have a half antinode on the left, a half antinode on the right to make one complete antinode. To get the wavelength equation, I'm taking my 0.3 length of the instrument times 2 divided by 1. So hey, these actually have the same wavelength for both problems. Totally a coincidence. So when I go get the first harmonic, I know the wavelength is 0.6. I'm solving for frequency, and the tube is filled with air. So because I know it's filled with air, the speed of sound is 340. That gets me a fundamental frequency of 566.7 hertz. So notice it was the first harmonic, the first wavelength, and so this must be the fundamental frequency. The next three harmonics are just multiples of that first one. So if the first frequency was 566, the next one up would be twice as big. I would do 566 times 2, 566 times 3. I think we get the pattern here. And that would get me the multiple frequencies. If the fundamental frequency is 556, then the next one is 1132, then 1698, then 2264. They're multiples of each other. So the next one up is times 2, times 3, and times 4. All right, everyone. Well, that's about it. Good luck on your final. Bye.